Okay, so it's a great day to be us because we're going to talk about trigonometric substitution. So this is a unique way to use substitution for integrals. So we use it as needed for integrals of a certain form, and I'm just going to give you a cheat sheet for what that certain form is. So if the integral involves a squared minus x squared, then you're going to substitute x equals a sine theta, and then you use sine squared theta plus cosine squared theta equals 1. If the integral involves a squared plus x squared, then you're going to set x equal to a tangent theta, and you'll use this trig identity here. Versus if you have x squared minus a squared in the integral, then you're going to set up x equals a sine or a secant theta, and you'll use this integration or this trig identity here. So the whole thing with this is that if you have something that resembles one of these forms, then you can go ahead and use the substitution. So let's go ahead and just jump right into an example. So I've got this integral of dx over the square root of 9 plus x squared. So I've got that 9 plus x squared. So as I look through this, that fits kind of that middle form here. And so in this case, then what that means is, so I've got 9 plus x squared. So my x is going to equal 3 tangent theta. Now, as far as like what do you do with the rest of this? The rest of this just flows like normal substitution for a while. So I need to, of course, find my dx, so I need to integrate. So my dx will be 3 secant squared theta d theta. And then what I'm going to do is I'm going to substitute all of these back into the original integral. So I get 3 secant squared theta d theta, right? So that dx now becomes all of this. So that can feel a little awkward, and I think sometimes that's like a common thing that people forget. But you're going to make this giant substitution on top, and then in the bottom, I'm going to have 9 plus 3 tangent theta squared, which of course, that 3 tangent theta squared can be rewritten as 9 tangent squared theta. And so now from here, having this 9 plus 9 tangent squared theta, what you'll notice here is that I can now factor that 9 out from the denominator. So see how I factored it out from those two terms? And so now I have this 1 plus tangent squared theta. And so that's where in this table, we had this other piece of information using this 1 plus tangent squared theta. This is now what we're going to use in this case. So what that's going to allow me to do is the 1 plus tangent squared theta is going to turn into secant squared theta. And so now I can also evaluate that square root. So that square root of 9 secant squared theta is just going to be 3 secant theta. So now you can also see that I've like really kind of shaken up this integral quite a bit. And what I can do next is I can cancel out the 3's, boom, boom, and I can cancel out one of these secant thetas. So this whole integral now just turns into secant theta d theta. And so from here, this is technically one of the integrals that in a lot of calculus classes you're just supposed to remember. So you can, of course, use substitution to finish this, but I'm just going to state the formula is the natural log of secant theta plus tangent theta plus c. Now, the whole thing to remember is that we're actually not done because we use substitution. So now we need to replace everything. And this is where things can get a little interesting. So remember, our original substitution was x equals 3 tangent theta. So what I'm going to do is first I'm just going to solve this for tangent theta. This is going to do a couple of things for me. So first of all, notice that I have tangent theta here. So now tangent theta can be replaced with x over 3. So I'm part of the way done with like working on this integral. But the other thing that I can do with tangent theta is I can actually set up a reference triangle. So I'm going to have this right triangle, here's my theta, and I remember that tangent stands for opposite over adjacent sides. So I can label this triangle then as here's my opposite side from theta and there's my adjacent side, so there's my two sides. And now that I know these two sides, I can also solve for the hypotenuse, so that's just going to be square root of 9 plus x squared. So you've got to know a little bit about your right triangle trigonometry to do all of this. Okay, and so now that I have all that information, so I still have to solve for this secant theta, right? So this secant theta I can think of as secant theta is the same as 1 over cosine theta. So cosine theta is typically adjacent side over hypotenuse side, or the hypotenuse side. So for secant, then it's just the reciprocal of that. So it's going to be the hypotenuse side over the adjacent side. So if I'm trying to figure out what is the value of secant theta, now I can just use my little reference triangle. So here's the hypotenuse, here's the adjacent side. So it's square root of 9 plus x squared over 3. And so now I can plug all of that information into where I had this secant theta and tangent theta. So my final answer, instead of being natural log of secant theta plus tangent theta plus c, it will be natural log of the absolute value of square root of 9 plus x squared over 3 plus x over 3, and then plus c. So that's the whole thing with substitution, trig substitution. Now, here's my question. Going back to our original integral, so it was dx over square root of 9 plus x squared. My question is there another way that I could have done this? So yes, so it kind of depends on the calculus class. So some calculus classes use hyperbolic functions, some don't. The one that I teach does. So this is actually just the integral. So this we could have just integrated right away. This is the sinh x over 3. That's what that would have been. And so now I'm going to tell you this great fact to use at a party. It's that the inverse of sinh of x over a is going to be equal to the natural log of the square root of a squared plus x squared over a plus x over a. These two things are actually equivalent to one another. And so the good thing to know about this actually is in the event that you either forgot what the integral of sinh was, or you just don't know it, these are equivalent forms. So if this is the answer that you use, that's all good. But what I am saying is that technically you could have not used substitution for this one and just gone straight to the answer. And so that's something that we want to think about as we're working through a bunch of these problems, okay? All right, so now I want to do another problem. So I've got the integral of x squared over the square root of 25 minus x squared. Okay, so for this one, so I've got that 25 minus x squared. So that is going to coincide with kind of this situation here. So what I'm going to do is I'm going to set my x equal, let's see, I'll use the white color. So I'll set my x equal to 5 sine theta. And so then of course my dx will be 5 cosine theta dx. Okay, now from here, what I want to recommend that you do is I actually think you know enough now to try this totally on your own. So I would try to complete the substitution and just see if you can finish the whole thing. Now, if you get to a point where you're like, okay, now I forgot where to go from here, that's totally fine. But try this on your own because I think you might be able to surprise yourself with how far you can get with this. Give it a go, hit play when you're ready. Okay, so whatever progress you made is great. So just trying it is enough, right? So I am going to go ahead now and replace my x squared with 5 sine theta squared. And then in this denominator, this will be 25 minus 5 sine theta squared. And then where I had this dx, now I'm going to replace it with that 5 cosine theta, d theta. Sorry, I wrote dx here. I meant to write d theta. Okay, cool. So now we can go ahead and we can kind of chug through this piece here. So this becomes 25 minus 25, can't write, sine squared theta. And I can factor out that 25 to get 25 cosine squared theta. So remember, each one of these substitutions typically have a specific substitution or a specific trig identity that you want to use. In this case, I'm using that 1 minus sine squared will equal cosine squared. So I just kind of rearrange this trig identity here. Okay, so then what I can do, let's see, I'll make some space. So I can rewrite this now as 25 sine squared theta over the square root of 25 cosine squared theta, and then don't forget all this other fun stuff over here. Okay, cool. So now we can simplify this square root. So this will turn into 25 sine squared theta over 5 cosine theta times 5 cosine theta d theta. And from here, now I can see those 5 cosine thetas drop out. I can bring this 25 out here, and I just need to integrate sine squared theta d theta. Okay, now this is your classic integration situation. So you do have to really know kind of some of those classic integrals at this point. The only way that you can integrate sine squared theta is you have to use the half angle identity. So specifically what I'm going to do is I'm going to rewrite this sine squared as 1 minus cosine 2 theta over 2 d theta. And now I can break this into two separate integrals. So I'll go ahead and do that. Okay, so I've got a little more space. I'm going to call this 1/2 minus 1/2 cosine 2 theta d theta. And so now I'll integrate. So this is going to be 25 1/2 theta minus 1 over 4 sine 2 theta plus c. Now, of course, we now have to actually go back and like substitute everything. So let's make some space to do that. All right, so here is what I've got, and I want to just remind myself what my initial substitution was. So it was this x equals 5 sine theta. So we're going to set up our little reference triangle. And so this is going to be 5 sine theta is going to equal x over 5. So if you think about your SOHCAHTOA, so this is going to be the opposite side over the hypotenuse side. So here's x and here's 5. And so then I can just use my a squared plus b squared equals c squared to get 25 minus x squared. Take the square root of 25 minus x squared. There's my third side. Okay, so now we have to finish the rest of this, right? So to figure out what is the value of just theta, well, I can do that from this relationship here. So the only way to find theta in this case is you've just got to use the inverse sine function. So this is the inverse sine of x over 5. But then what about sine of 2 theta? Okay, so there's going to be another trig identity that is suddenly very useful for trig substitution. So I feel like this one you don't use a ton until you get to trig substitution. So if you're in my class, I would expect you to know this. I think that a lot of calculus classes would just expect that you start busting this out. If you forgot it up to this point, that's totally fine, but I'm just telling you, it's something that you need to know now. So that identity is that sine 2 theta equals 2 sine theta cosine theta. So the only way that you're going to be able to solve this one for sine 2 theta is really by using that identity. So I am just going to go ahead and set that up. So it's 2 sine theta cosine theta. And so from here, now I can pretty easily like figure out my reference triangles. So sine theta, remember, we already set that up, right? Sine theta we said equals x over 5. So then what's cosine theta going to be? Well, here's my theta. Cosine is adjacent over hypotenuse. So here's my adjacent side, here's my hypotenuse. So this will be square root of 25 minus x squared over 5. So there's all the pieces that I need. So just to kind of recap, so for my theta, I'm going to use this. And for my sine 2 theta, I'm going to use all this, okay? So my final answer then will be 25, let me change my color here, 25 1/2 sine of theta x over 5. And then remember, this was 1/4. Actually, I'll just write it all out. So this is 1/4 times 2 x over 5 square root of 25 minus x squared over 5, and then all of that plus c. So obviously I'm running out of space here. Sorry about that. So, okay, so let's now put these pieces all together. So this is going to be 25 over 2 inverse sine of x over 5. And then let's see. So for this 2, this will cancel out with this 4. And then this 25 will cancel out with these 5s here. So I'm left with on top x square root of 25 minus x squared over 2. And then all of that plus c. And that is the name of the game for that one. Okay, so just to kind of keep you on your toes here, so starting with the next one, so I have this integral dx over 50 plus 2x squared. So the thing that's kind of screaming out at me for this one is something could be factored out. So what I want you to do is I actually want you to try this one totally on your own and just see if, like, evaluate it, think about what do you want to do with this one, just give it a try and then hit play when you're ready. Okay, so the thing that's kind of screaming out at me is I can factor 1/2 out of this. And in factoring that out of the bottom, that leaves me with 25 plus x squared. And the other thing actually that I noticed with this is, so this is another one where, yeah, I could use trig substitution here, but I actually don't need it. This is one of like the known integrals. This one would just be inverse tangent. So this is going to be 1/2 inverse tangent of x over 5. Oops, and it should be actually 1/2 times 1/5. So I can just evaluate for these bounds here. So this becomes 1/10 inverse tangent of just 2/5 minus 0. That would actually just be the answer for this one. So like I said, I'm keeping you on your toes about whether you actually need to use trig substitution. Now, if you use trig substitution, you would have gotten the same answer. It just would have taken you longer. So I have one more problem that I want to go through in this lesson, and I specifically want to talk about that you can combine substitution and trig substitution. And so it's not always obvious that you're going to do this. So first of all, if I look at this integral here, I would not initially think that I'm going to use trig substitution. This feels more like substitution just because of the different square roots. And of course, you might start by first factoring out, let's see, this square root of x from the bottom. Now, I would probably start by trying to substitute a few things. And this is one of those problems where you're going to have to make a few guesses with your substitution and troubleshoot your guess a few times to see if you can get it. So I think this is actually a really great one. I want you to try 2 ideas to see if you can substitute everything that you see in the problem to start. So be a little creative with it. Make your first guess, and if that does work, that's great. And if it doesn't work, try to troubleshoot and make a second guess before I show you the answer, and then hit play when you're ready. Okay, so for this one, so there's, if you tried anything, that's great. I think this is kind of a tricky one. So the best guess actually for this one is going to be to use my u equal to 2 square root of x. And so then my du, of course, will be 1 over the square root of x dx. Okay, so there's a lot of reasons as to like, there's a lot of troubleshooting I think that goes into like, why would you even choose this? So if you try to choose anything else, so if I try to choose like u equals 1 plus 4x, okay, my du is just going to be 4, and then I'm going to run into this issue with having this square root of x. So you can see right away that it's definitely not going to be this 1 plus square root of x. You'll also kind of get this hint, like, okay, maybe it has something to do with the square root of x. And you might get then that this is 1 over 2 square root of x, and this is a great guess if that's what you did. The only reason why I include the 2 in this case is because of squaring. So specifically, what is u squared? U squared is 4x, and so it is just because there is a 4 here that I can make a slightly stronger guess. And you'll notice now by putting that 2 in front, it actually makes my du much better because now I can substitute out this piece here. So any guesses that you made on this, and even if you didn't make any of these, it's all about just making progress. But hopefully you can kind of appreciate, that's always the biggest thing with this, is to not get frustrated, but instead just to kind of try to appreciate the like how we shot our way into that. This was a really good guess. It's just a slightly stronger guess to choose this one. Okay, so I'll clear some space. And okay, so now I'm just going to write my integral over here for a second, so without the limits of integration. So this is going to be 3 over 1 plus u squared du. Again, because my 4x is right here, and then my 1/2 dx is going to be this part and this part here. So all of that substitutes out nicely. Now I also want to sub out my limits of integration. So if x equals 1/4, then u will equal 2 times 1 over 2, so that'll equal 1. And if x equals 1 over 12, then the square root of 12 will equal 2 times 4 square root, 2 times 1 over 2 square root of 3, so this will equal 1 over the square root of 3. So the other thing that I'm going to do here is I'm going to change my limits of integration, because why not? Okay, good times. So now let's make some space and let's keep going. All right, so from here, you really don't need to use trig substitution for this one, but I actually do just want to do it just so I can kind of show you, in the event that you look at this and you don't recognize that what the integral is, it all works out fine. So, okay, so now what I'm going to do is I'm going to use my trig substitution, so I know that I need to use this form here. So my x in this case, which maybe I want to call this something else, I guess my u in this case, right, will just be tangent theta. So then my du is secant squared theta d theta. And also, so in doing this, this is a definite integral, so we can also change our limits of integration again. So if u equals 1, then my tangent of 1 will equal, sorry, wrong order. So if my u equals 1, so u equals tangent of theta, so we have to actually kind of think about this. So if u equals 1, you're actually going to have this relationship here. So it's not plugging in now, right, because it's just that u equals. This is what we set u equal to, so here's my u equals 1. So then I have to just go through and I have to use an inverse trig function to figure this out. So the inverse of tangent of 1 inverse is going to be pi over 4. And then if u is 1 over the square root of 3, so again, if I have this relationship of u equals tangent of theta, so 1 over the square root of 3 equals tangent. So when is that true? Well, we have the inverse tangent of square root of 3 over 3. That will equal pi over 6. And you can just use a unit circle to help you with all of that. Okay, so now I have a whole bunch of substitutions to make again. So let's go ahead and do that. So I'll make some space. Okay, so I'm going to go from pi over 6 to pi over 4, and then I've got 3 over 1 plus tangent squared theta, and then my d theta, remember, was secant squared theta d theta. Okay, and so now, so remember, 1 plus tangent theta equals secant squared theta. So if I continue on with this now, so I've got pi over 4 and then this pi over 6. This is going to be 3 over secant squared theta. And so the reason why, it's not horrible if you do trig substitution with some of these, even if you could have done it another way, is now you can see actually this got a lot simpler, right? So all I'm integrating at this point is just 3. So it will all work out the same. So I get 3 theta, and then I need to evaluate for my limits of integration. Okay, now here's the other beautiful thing, and this is also why I wanted to do a definite integral with this. So if this were an indefinite integral, so then I would have to go back and solve for theta. And remember that theta ultimately equaled the tangent function, so you would get that this ultimately equals inverse tangent. So if this were an indefinite integral, we'd get inverse tangent. It just took us a little bit more work to get there. But now that this is a definite integral, so here's actually the great thing. I ended up canceling out everything, and I've changed my limits of integration, so I don't even have to deal with the trig functions anymore. So this could be a really strong reason for changing your limits of integration. So then I'm just going to take pi over 4 minus pi over 6. And so let's see. So that's going to be 3 pi over 12 minus 2 pi over 12. So let's see, I end up with 1 pi over 12. So this is just going to end up equaling pi over 4. And that's actually much better, that's a much easier way to kind of evaluate everything. So is it the best way to do it? I don't know, it's up to you. So it's tomato, tomato. Some of these things are just preference. And some of these things, it's like you didn't really know where this is going. So sometimes some of these things are just kind of an exploration and you're just seeing where it takes you. So I have a lot more videos beyond this, but I like to keep the lesson videos a little bit shorter. So if you found this helpful, I'd love it if you hit the like button or the subscribe button. But also you can check out my other example videos. So I do a lot more examples in some of the other videos. So strongly recommend you check those out. But otherwise, I'm going to leave it at that, guys. I hope to see you in another video. Bye.